Luba Tang, and now I'm starting up a new company called SkyMiser, founder and CEO of SkyMiser. Today I will give you my presentation. It's about a linker, board optimizing linker for BSD. Okay, this is today's online. Today we'll go to introduce the board project, our linker project, and then we'll go through a linking theory. It will about linking language and fragment reference graph. And finally, I will present our plan and schedule of the board project. Okay, and this is me, I'm Luba, and I was the architect of AsiaBSDCon and Marvel iterative compiler. Yeah, my expertise is compiler and linker and electronic system level design. Okay, now you must wondering that why we just need a new linker. Actually, there are three reasons for developing a new linker. The first is BSD. Now you know BSD is currently switched to a BSD licensee tool chain, and the linker is the final frontier of the BSD licensee tool chain. And the second is interesting is VMs, especially Android VM. Take for example, Delvik and Random script. And those VM are switching to a new technology we call ahead of time compilation, AOT. And if you have ever been studying the compilation theory, you will know AOT is the ultimate solution of virtual machines. And Delvik now you have a new Java runtime called Art. Some of my members are joining this project, and the Art is a half-time compilation. And the script is now switching to AOT2. And the second reason is the heterogeneous multi-core system. As the advance of a GPU system, GPU language in the before was compile the bytecode at runtime. This is very time consuming. In order to save the runtime, they are going to switch the compilation to so-called two-stage compilation. And they will try to do a half-time compilation at the installation time. And for the GPU system, there are some problems about the memories. Before, GPU used external memory, but just found this year, CUDA will switch to a new memory format. It's called unified shared memory. GPU and CPU will share the same memory layout and use the same memory space. And this change will lead a lot of problems in the memory sharing. So they need a linker to handle about the memory space. Okay. So what the board project want to do? Okay, we just accept this new linker challenge. First, we want to do a modular and a reusable linker. Because for the virtual machines, they cannot use linker as a tool. They have to use linker as a library. So modular and reusable is very important feature for such kind of usage. And the second is the memory handling. Because for the heterogeneous system, unified shared memory. Okay, thank you. Okay, unified shared memory is very important, and there are some problems. For example, if you want to share pointers between GPU and the CPU, and if a CPU is 64 bits, but if a CPU is 64 bit, but a GPU is 32 bit, then they need some. Okay, thank you. And then they need some facility to switch these two memory space. And the linker may be the best guide at the position to handle this. And one of the goals of both projects is the on-device linking, because for the argument reality, it must run on mobile device, and mobile device has only limited computing power and memory, so the linker must be very small and very fast. So this is also the goal of both project. And then finally is the link optimization. Actually, most linker only do a few optimization for programs, but from the academic research, we know there are a lot of opportunity to optimize program at linking time. So one of the main goals of both projects is to do a link optimization. Yeah. So we can see this graph. The goal of both projects try to be the bridge between compilers and many different kind of processors. Compilers can maybe leverage different languages. For example, Delphic can pass Java, RenderScript and OpenCL, and all of them by board, they can share the same memory layout and use the uniform shared memory and dispatch the different computation to different processor. Yeah, this is the goal of the both project. Okay, now we are comparing the existing ELF linker. Actually, there are only 3 ELF linker can say full-fledged. The most popular is GNU-LD. It is GPL linker, and it can support almost all mainstream device. And its object format it has support rich object format, include bookcode, A.out and ELF, but the line of code is very huge. It's about 500,000 lines of code, and its performance is also, take for example, if we are trying to link web key, it may need 1 minute to link the whole web key. And but it is good. It has a good design. It has intermediate representation. Users can leverage this intermediate representation to do some optimization. The IR we call BFD library. But however, because BFD library is not really easy to use, so the optimization of GNU-LD is really few. And because it is very huge and memory consuming, so it is almost impossible to use GNU-LD in the mobile device. But on the other side, we can see Google Gold. Google Gold is also the GPL license, and but it's only targeted to some kind of platform. Actually, Gold support only those platforms who has single global offset table. For example, ARM and x86. But the MIPS and Spark they need multiple GOT, so they cannot be integrated into Gold. And the Gold is ELF only, but the Gold have better code quality. It's only 100,000 lines of code, and Gold use a new algorithm to linking, so it's really fast. It's about 200% faster than GNU-LD. However, Gold do not have IR, so it's really very difficult to implement any kind of optimization in Gold. So it only have ICF such kind of optimization, and it is also memory consuming, so it is impossible to use Gold on mobile device. Okay, let's look NCLinker. I was the architect of NCLinker. NCLinker, first, it is BSD license because it have to be run on all Android device, and Google acts as must release it as BSD, and it can support all kinds of Android device, including ARM, x86, and MIPS. And now it also can link 64-bit Intel and MIPS and a special DSP target called Hexagon. It is developed by Qualcomm. Although NCLinker now it is ELF only, but its format is extensible. We want to extend it to Mach O. Actually, its IR is more close to Mach O, and the code quality of NCLinker is really good. We use only half of line of code of Gold to implement the whole feature of Gold. And currently it is still the fastest linker in the world. It's static 200% of GNU-LD and 13% faster than Google Gold. And it have rich IR, but however, it does not have any optimization. But its memory consuming is very small and it is very fast, so it can be used on mobile device. Now, okay, Then what is both want to do is that we want to keep all the advantage of NC-linker, and we want to improve the optimization of NC-linker. We want to leverage some special optimization like a layout or hard code reordering in our board linker, and of course it must be small and fast to be able to run on mobile device. Okay. Now, actually, linker is very, very intricate. Only in this world, only few teams can make a full-fledged linker. There are only few open source linker that can be said full-fledged. Actually, there are only 4. GNU-LD and Google Gold and NC-linker. These 3 linker now can link the Linux kernel. And NC-linker is exempt to link the BSD kernel and BSD build world. And of course, it is born for Android, so it can link Android system. And Apple LD64 can link Mac OS X and iOS. Okay. Besides system link, actually ELF link is super complicated. There are a lot of undocumented behavior. Take example for weak alias. Actually, the behavior between GNU-LD and Gold are also different. So, actually, and many features are undocumented, just like somebody have an idea and he just implemented a feature in the GNU-LD. So, actually, if we want to make an ELF linker, it's very, very tough and very, very difficult. Okay, and the difficulty stops researchers to develop their optimization algorithm in linkers. So the goal of both project is try to provide a easy use and helpful IR for the researchers to develop their optimizations. Okay. Now this picture is true. This picture is about performance. Okay, we can see a blue bar. The blue bar is the baseline. Baseline is GNU-LD. It's 100%, and the red bar is Gold. Gold is about 200% faster than GNU-LD, and the green bar is NC-linker. NC-linker is about 30% faster than Gold. And the interesting thing is that almost okay, the output quality of all the amount of this linker is almost identical. Actually, the difference of performance is less than 3%. What does that mean? That means actually most existing link optimization doesn't work. Yeah. So and in academic research, there are some useful research, but cannot be implemented in the current existing linkers. Okay. Now we are going to our about the linker theory. Okay. Why this optimization cannot be applied in this linker? Because because this linker does not provide good IR for researchers. So we are going to introduce the IR for the board. Okay. The first board provides so-called 2 layers IR. We provide one is called linker command line languaging, and the other is fragment graph. I will explain this later. And what is fragment? Fragment is the basic linking unit of a board. It's just a block of instruction or block of data. It may be a session, maybe a block of code or data, or just an individual symbol of its code and the data. And we wish both can track the link time for the output quality. If we want a better output quality, then we can just use more finer granularity, and we can apply may need more link time to apply this optimization, but we can get better output output quality. But if this link is used on mobile device, then we must concern about the fast linking. So we will use a cross-grain linking unit to get a faster link time. Okay, now we'll go to our first IR, so-called linker command line language. Actually, linker command line is so complicated. It is just a kind of language. Why is it a kind of a language? Because the meaning of the command line option depends on their position, or depends on the position of the other option. Okay, some option also have its own grammar. Let's take this for example. We define 4 categories for this option. The first is input file. And take this for example. This command line is try to link these 2 objects. One is called XXX, and the other is maybe a shared library or pthread. And one is attribute. Attribute will control the behavior of, will control the attribute of the option immediate after its attribute. And some option like linker script option, it has its own grammar. And some is general option, it is target in position independent. Okay. So we know the command line of the linker command line is so intricate. Now we see, we review all the other linkers to see how do they pass this kind of language. The first is GNU LD. GNU LD, it passes the command line just like an interpreter. So it's just to pass the command line and read the input file one by one, and try to link the whole object one by one. After it completes the parsing, then we can get the output. Okay. Google Gold is interesting. It tries to separate the interpreter into 2 paths. The first path is still an interpreter, but the second path, it has a test queue, and the first path, the stage 1 will try to analyze the dependency of this option and of this task, and in the stage two, all these tasks will run in parallel. So Go is so fast because it is first linker to decide to run on cluster, but actually the dependency of these tasks are too high. So Go is almost, even we try to turn on all thread, but Go will behave like a single thread linker. And the third is nginlinker. In nginlinker, we will try to separate the linking process into different stages. Yeah, we will expand this stage later. And what in bold? In bold, we will find this stage and separate this stage into more fine grain. And the more fine grain can help the researchers to improve their optimizations. Okay. Now we will expand. We will try to define the command line language. The first thing we have to know is the input file. Input file of a linker may be an object file, an archive, or a linker script. And then some input files can be defined multiple times. Take for example, if we take WebKey for example. In WebKey, the C library is being linked about 4 times, and the C library can be linked again and again. And the result of a linking, the result of a linking output depends on the position of the input. That's why because we have 2 kinds of behavior. The first is the weak symbols. Weak symbols is a first come first serve symbol. Linker will keep the first weak symbol he reads. So if we change the position, of the input, then the definition, the output of the weak symbol will be different. The other is condensation. Condensation is used to emulate the inline function of C++ language. And in the inline function, and the link compiler will try to produce many many copy of the inline function into different object files, and the linker will keep the first inline function it meets. So in condensation is also first come first serve. And these two behavior are position dependent. And then there are two semantic to read the input file. The first semantic is input. Let's just tell linker to read the input one by one. The second is group. Linker will read the group over and over, again and again, until there are no new undefined references are created. Take this for example. There are two archives, archive B and archive C in this group. And the linker will read object A first, then read archive B, archive C. Then if there are new undefined reference, the linker will go back to read the archive B again and read the archive C, and over until there are no new undefined reference, and then go to read the object D and object E. Okay, so by this behavior, we know we can get the command line. Actually, it has some kind of grammar and some kind of position, relative. So it can be modeled as a language. Okay. In AsiaLink and both, we will model the command line as the input file tree. Okay, the input file tree is a tree. All the vertex of the tree is the input file or group, and the edge is a relationship between these two vertices. Take this for example. Okay, in this linker command line, the output input file tree is like that. Okay, we can see in this tree, every vertex is an object file or archive or a group. And there are two kinds of relationship. One is positional. Take a list for example. Object D is immediate before object E. So there is a positional edge from D to E. And we know archive B and archive C belong to this group. So there is an inclusive edge from the group to the archive B, the first archive in this group. Okay, by this definition, we can convert this command line to the tree structure. And as we mentioned before, there are some attributes of the input file. Actually, because the attributes of a linker are, there are only a few attributes of a linker, so we will try to enumerate all attributes in a whole node. Take this for example. There is an attribute we call the whole archive. This whole archive tells linker to link every object files in this archive to the output. Okay. And we know only archive B and C affected by the whole archive option. So there is an edge from the archive B and archive C to a whole attribute, and the other objects do not have this attribute. So the other objects points to the not whole archive attribute. Okay, by the definition of input tree and archive, we can model the input files as a tree structure. Okay, and this is the now we are going to define the process of linking. The first stage of linking we call normalization. Normalization is a process to transfer the command line language into the input file. So it will pass the command line option. It will recognize the input file format to know it is archive or it is object, and then you will try to merge all subtrees to find a single common input file tree. So it is just a bottom-up algorithm. We will try to build up all subtrees and merge them together. Okay, how to use the input tree? Actually, input tree is very useful for some simple optimization. Take for example, take a simple resolution for example. Simple resolution, we can just traverse this tree by DFS search. And because simple resolution, the symbols, the weak symbol is first come first serve. So we must use DFS to keep the correctness of the output. But for session merge, we can try to use BFS. That's for better cache locality. That's why. If we just take this for example, if we are using BFS on this tree, then the first is ADXYENO, and we will find that the objects in the same level, the first level objects are user-defined objects, and the second level is the library, and the behavior of human programming is that we will try to the program have spatial locality and temporal locality, so it will be run faster if we can put the program the program that frequently used together. So if we use the BFS, then object O and object D will put much close to input the locality. Okay, then after normalization, the next stage is the resolution. Resolution is a process try to resolve the symbol and read the relocation. Okay, now we are trying to define our fragment reference graph. Okay, as we mentioned before, the fragment is just a block of instructional data, and the fragment is very flexible. It may be a function, a label, or just a single data. And actually, let's take this graph to example. There are two modules. One is module X, and the other is module Y. And in the module X, there is a global variable we call A. So there will be a symbol. And in module Y, there is a function called bar. So there will be a symbol bar to indicate that here is a function bar. And there is another symbol A to indicate that here is a variable A. Okay, and if in function bar, there is an instruction use the variable A, then compiler will generate a relocation entry to indicate this associated data need to be changed to adjust its address to the correct variable. So by the compiler theory, we'll know relocation just represent a use-defined chain, a use-defined relationship. We can call module Y as a use fragment and the module X as a defined fragment. And the relocation is just represent the use-defined relationship between two fragments. Okay, so what is a reference? In Bold and in NCLink, a reference is defined as a symbolic linkage between two fragments. It is used to represent the use-defined chain that's produced by compiler. So a fragment is a direct edge from the use to a define. So if here is the use fragment, here is a define fragment, there must be a relocation entry between these two fragments. And we will define the a reference from the use to a define. So both will represent the input modules as a graph structure. In this graph structure, every vertex is a fragment, and every edge is a reference. Okay, so this is the mathematical definition of the fragment reference graph. It's just a digraph, a directed graph. And this is a focal. It has 4 sets. The first set is a set of fragments. It represents to a vertex. And E is the set of reference from it is a directed edge from use to define. The third set is S. We call it define symbols. You can say it's a star. It's star vertex. It represents the entrance of this graph. Take this for example. This may be a Okay, libc, and libc may have two functions, one called star and one called underline global, and there we must to define symbol to indicate here is the entrance of a star function, and here is the entrance of a global function. So S is just the set of this star symbol, and O is the exit of the entire graph. We will explain this later. Okay, so let's redefine symbol resolution. Okay, in all the other linkers, symbol resolution is just very confusing. Actually, GNU LD and Gold have different definition of symbol resolution, but in AsiaLink and Bold, we use mathematical definition to define symbol resolution. What is symbol resolution? Symbol resolution is try to determine the topology of a reference graph. Take this for example. For every use fragment, that will be a relocation, and the relocation will be indicated by undefined symbol. And what is symbol resolution? Symbol resolution is try to find out the topology of the whole graph. It's try to answer this question: which symbol is the real symbol this undefined symbol must be linked to? So by this definition, we can simplify symbol resolution just by connect or use and define to build up the tree. Yeah. And there are some optimization opportunity on the fragment reference graph. The first is fragment stripping. By this graph, we can try to find out the reachability of this graph. There are some fragments and some symbols that never be reached, and we can just strip this code. And the other is the branch optimization. If we can, we can just change the type of relocation to change the type of relocation. Then linker will also change the content of use fragment. It will use the branch, low cost branch to replace a high cost branch. And some optimization like ICF, Gold also has ICF, and for TLS, straight local storage, there are some optimization can be done here in this stage. Okay, and the next stage is layout. Okay, with this graph, although we have this graph, we still not have the order of all fragments. So what is layout? Layout is a process to find out the topological sort of a fragment reference graph. Okay, and before mentioning the algorithm of layout, we must mention the last part of a fragment reference graph, the exit. Okay. Actually, there are only two kinds of architecture in this world. One is called, I just call it ARM and Intel. It is so-called a single GOT model. And the other, the main player is MIPS. It is used so-called global address table and with multiple GOT. Okay. And the main difference between okay, and we can just abstract the common feature of these two kinds of relocation model just by our exit. Okay, what is exit? Actually, take this for example. If this is a program A, and this program A need to use the function B, take example to call printf, and the printf is in the outside module, then there must be a GOT entry to a GOT entry and a dynamic relocation entry. The loader will pass the dynamic relocation entry to find out the address of this function and put this address to GOT. When this program runs to the code, it will use indirect jump and to read the content of GOT and to get the right address. So what is exit in the fragment reference graph is a pair of GOT and dynamic relocation. And it means the exit of the reference graph. Okay. So layout is easy. It is just try to sort the fragment reference graph topologically and try to assign the address to fragment, symbol, and the GOT. And both Gold and NCLink will follow the terminology of Gold. So we will use relocation scanning and the pre-layout. Use these two terminology to represent the calculation of the size and the topological sort. Okay, and the next important stage is relocation. Okay, after layout, we have a topological sort. Now is it time to assign the real address, real offset to all fragments and symbols. So relocation is try to finalize the address of symbols and try to apply relocation to address the used fragment. Okay, what is apply relocation? Take this for example. If module Y use the variable A, and there will be a relocation between the used fragment and defined fragment. What is apply relocation? Apply relocation is try to adjust the content of module Y and adjust to the target symbol address, and just remove the relocation. Okay, there is although the people will say relocation type is target dependent, but actually almost all relocation type will follow this formula as subtract P and add A. What does that mean? Okay, after layout, we have already in a linear address space, and here is a relocation to indicate this instruction will use this variable, and S is the address of symbol, so it is symbol A. P is the address of a use instruction, so the meaning of S subtract P is try to find the distance between the use and the defined fragment, and the A is a really target dependent part because for different machine it have different instruction format. Take this for example, the target operand may be in the third byte of the instruction. So A is just adjustment, addend to total linker to adjust this address. Yeah. So this is a formula of apply relocation. Yeah. And the opportunity for optimization on layout, these are the optimization on layout. We can try to do the pre-linking. Okay, pre-linking there are two kinds of pre-linking. One is dynamic pre-linking. The other is static pre-linking. Okay, dynamic pre-linking is just used by all the Android. It's just try to fill the target address to all GOT entries, and you must know some Windows systems are always faster. That's because Windows system, Microsoft Windows system use the static pre-linking. It's just try to remove all GOT and use the direct link and direct change and direct ref to a fixed address without any exit. So static pre-linking was faster, 30% faster than dynamic pre-linking. And there are some interesting optimization like symbol stripping. We can strip all unused symbol to reduce the code size. And some layout optimization like session function basic block reordering that can improve the performance about 30%. Okay. And then the last stage is the emission. all the stage we mentioned before is format independent, and emission is try to add the format information back to the IR. So emission is just to output the format. In the NCLink design and in the Gold design, in the bold design, we can support various format. So although currently we only support ELF, but actually it can easily design to support like Macro and COF. Yeah, and here are some tricky to input the cache and the page located here. Okay. Now we go to the last part and the status and the schedule of the both project. Okay, current status. We developed both just for a couple of months. We start from last Christmas, and now we already finished the building system and the testing framework. We use the auto tools like AutoConf, AutoMake, and it's welcome. Any contribution is welcome to help us to integrate the CMake part. And we use in both we use a special unit test library. We call this PET. PET is a performance analysis toolkit. It's try to leverage the hardware performance unit and the unit test. So by PET, we can just write a typical case of a board, and we can get precise performance information to help us to input board. And now we are trying to build our ADT abstract data type and our OS and environment support library. Okay. Unlike NCLinker, board is right from scratch, so we don't twist with LVM. This can help the other groups like Fedora or BSD group more easier to port board to their environment. But the architecture is very similar to LVM. We are following the same coding style. Okay, and this is the rough development plan. And now we are developing the infrastructure. And the next stage is a simple tool called NM. We can just show the information of our symbol. And the next stage is incremental linking, then share library, then executable format support. Okay, and this is roadmap. The gray bar is what we have already done, and the green bar is what we are doing. The yellow one is what we are planning to do. Now we are trying to implement all ADT and support like binary tree, memory allocator, and file handler, because linker is interesting program. It will try to read the file system. It will try to touch file system over and over. So a good file handling is very important for linkers. And after we finish the basic ADT and the support, we will try to put a target and format infrastructure in there, and then we will try to implement the fourth stage. Hopefully, we can support NN when we complete the resolution part. Okay, here is a detailed schedule, and now we are here. We are just trying to complete our infrastructure, and after the infrastructure, the next is the normalization and the resolution. And when we finish the resolution, then we can get NM. And the next is the layout and the relocation. After layout and relocation, we can get incremental linking. Then we will put all our focus on the target-dependent part. And after target-dependent part, a share library can be done. Yeah. So the plan is to release a prototype at October. Yeah. Okay. Thank you. And this is my presentation. Here is the project site. We use Google Code. Welcome to visit the website and give any comment are welcome. And here is our mailing list. Yeah. Thank you. Any question? Oh, okay. Thank you.